Hello student, welcome to our physics discussion, that is physics in a smart way. We consider today a topic that usually our textbooks of class 11, they got a chapter that is work, energy and power. And this topic, which is center of mass or center of gravity, in short some people say centroid, but when somebody is using the word centroid, is more towards engineering or advanced, bit advanced. So central mass and central gravity, that is usually discussed in the context of work, energy, power in that topic. Though it has got no direct connection, it is related to work, energy, power, to other topics of mechanics also, but usually they include it. Okay, that is the preamble. So central mass as it is there, some people try to define central mass. It is a position inside an object. It is a position inside an object where the entire mass of the object can be assumed to be concentrated for all practical calculations. Mark my words. An object must be having masses everywhere inside it. Everywhere object has got molecules and atoms. Okay, so mass is present. Mass is distributed in the object, however small or however large it may be. But when somebody defines central mass, it says we assume that the entire mass of the object is assumed to be concentrated at one point. At other points, there is no mass. And we know that's a mistake. We know that's a mistake. That presumption is wrong, horrendously wrong. But still then, we hope our calculation will be correct. So thereby, we know that's a bit intelligent job. We assume that the entire mass is coming to a point or considered at a point which is not in fact so, but still then to simplify our calculations we can assume so, but that assumption of the point, that selection of the point must be so cunning, must be so cunningly done so that we got all practical calculation correct, even if masses are distributed, even if the if somebody considers all the molecules, all the atoms of the body, in place of fixing up the entire mass at one point, he or she will be having the same calculation. Okay, so thereby, as you know, center of mass is an imaginary point that has got no reality connected to it. Similarly, center of gravity is the point. If we replace the mass by gravity force, you know, every mass in the presence of a big body like Earth and all that has gravity attached, has a gravity field, and within the gravity field, if a mass is there on every atom and every molecule, we know weight must be acting, gravity force must be acting. The formula, as everybody knows, is mg, and central gravity is similarly defined. It is the point where the entire gravity force can be assumed to be concentrated. Entire gravity force or the entire weight of the body can assume to be concentrated without any practical error or without for all practical purposes. Okay. So combinedly, if you combine center of mass and gravity, that becomes centroid. But initially, for some time, we'll be using different words, center mass and center gravity. Okay. I think you got the idea. So we now got a way to approach the topic, how the topic can be, or how we can be entering into the issue, or how that thing can be approached. Okay, as you see in the diagram, but before going to the diagram, let us have some issues straight. That is a quantity, a physical quantity known as torque. Known as torque. At advanced level, people put it as movement. So you may use the word torque or moment, but usually in 11 textbooks, they usually brand it as torque. The symbol they put down for that is tau. The torque shows the so-called rotational efficiency of a force that this thing we get to know in our topic of rotation dynamics or during rotation. So if a force causes somebody to rotate, and there are many forces, and when you compare the capacity of those forces to produce rotation, then you have to consider torque. Basically, torque can be expressed as a physical quantity which expresses capacity, or so to say, efficiency of a force to produce rotation. And torque is discussed vividly there. So very simply, to find out the torque, we try to find out if, let us say, body is rotating about a point which is given at the left and the force is there. So to find the torque, we multiply force with the perpendicular distance. From the point of rotation, we draw a normal. We multiply the force with the perpendicular distance from the point of rotation. And that usually is known as moment arm. The perpendicular distance is usually branded as moment arm. Don't confuse that with momentum, that is moment arm. So when you multiply torque, when you multiply force with the moment arm, then you get the torque. Okay, there are other ways using cross product and all those to find out, but basically the simplest or the easiest or the most physical, most handy way, practical way to find the torque is to multiply force with the perpendicular distance. That is moment arm to find the torque. Okay, our issue of torque is over. So what the torque is? The torque is the rotational efficiency, how a force is capable of producing rotation, that is expressed by the torque. So now we get to our diagram. I am taking the help of gravity because thereby it is bit practical and easy to understand, and thereby it will be helping us in grasping the idea more quickly. It doesn't matter whether we are using central gravity per center of mass or central gravity per central mass or central gravity. Doesn't matter. The basic thing is that whether idea goes into our head or not. Let us say we consider this red line is a weightless bar, a bar having no mass, a bar having no mass, a very small mass which can be ignored or neglected for practical purposes. This is a bar, long bar rather, and the bar is pivoted or hinged at the point A. Hinge or pivot is a connection which allows the rotation to be free, but that doesn't allow any separation and all that. Just like your door frame and the door, they are hinged. Window frame and the window, they are hinged. If you try to pull window out, the window won't be separating from the window frame. But window can rotate very freely around the thing. So that is in our native language, that is known as kabja. That is known as kabja. So hinge is a connection which allows rotation to be free, but doesn't allow linear motion, doesn't allow separation. So this red bar can rotate very freely in the plane of our paper about the point O. It can rotate very freely like this. It can rotate very freely. And on the bar, we hold the right hand on the bar. We have put several point masses. The point mass is M1 placed with an x coordinate x1 or at a distance x1 from the origin. The mass is M2, another mass is M2 that is placed with a position that is x2, similarly M3 having x coordinate x3 or 2. There are other masses also, or 2. The last mass we assume that is nth mass. So that is placed with the x coordinate or with a distance from the origin, so to say. If you consider this as x-axis, then that becomes y-axis. If you consider this as x-axis, that lies along the bar, so that becomes y-axis. Okay, so all the masses M1, M2, and M3, M4, and all those things, they will be having their weight. M1 will be having its weight, that is M1G, M2 will be having its weight, that is M2G, M3 will be having its weight, that is M3, similarly. So if you consider, and what is your force? If you consider the torque effect, the rotational effect, all those weights, so then we say the sum of all torque of all the weights will be equal to M1G x1 plus M2G x2. This is the force, that is the distance, permanent distance. This thing goes on, up to the last mass, that is MnGxn. That may be a long series. Okay. Now, a student try to think like this. He or she thinks like that. Instead of going for that long series, if I assume the entire mass of the bar, entire masses, all the masses is concentrated here. And because all the masses is concentrated here, so now the mass present here must be M1 plus M2 plus M3 up to Mn. So thereby, if you branded the mass as sigma m, the sigma m will be equal to the sum of all masses. Sum of all masses we have kept on the bar, M1 plus M2 plus M3 up to, so to say, the series goes on up to Mn. Okay, and that mass will be having its weight, which will be sigma m into g, and that weight will be acting downwards, and that weight will be also creating a torque effect about the point O. So, and as our logic says, the torque of the entire mass is one thing. We have not fixed. This position. The position, let us say, that is xc from the center. I'm not going to repeat anything on xc, where it is placed and all that. So if I find the torque of the entire weight at one go, then that torque of the entire weight will be equal to sigma m into g into your xc. And if this torque will be equal to this torque, then xc is the true center of mass. If I put the entire mass at the true center of mass, then you know that will be creating the same effect as the masses are doing individually. So thereby, as it is logically evident, sigma m into g into xc must be equal to on the other side, your m1g into x1 plus m2g into x2 plus the series goes on, your mn g into your xn. Sorry. I have to change the color. So as you can see, this is sigma m. Sorry. This is sigma m. Okay. Clearly, we can see G can be taken common out of the right hand side and can be cancelled on the left hand side. So thereby, we can clearly see, let me remove this space. On the left hand side, we can have sigma m into xc will be equal to m1 x1 plus M2X2 plus M3X3. You must excuse me, my marker pen doesn't cooperate. Plus, this series must be going on till it incorporates the last mass, that is Mn xn. The right hand side can be made shorter as sigma m into x. Sigma of mx. Sigma of mx means that is 1x1 and 2 is 2 like that. So now if you separate out, the formula of xc comes out. The formula of xc comes out. If we separate, then xc comes out to be, on the right hand side we call sigma mx by this quantity sigma m must be sending to the right hand side. And upon elaborating, we know this means that is m1x1 plus m2x2 plus m3x3. That series goes on till the last mass is over. So to say m1 plus m2 plus m3. You know, the last mass must be taken into account. This way, so now we see our calculation gives us a formula to find out the x coordinate of the center of mass if the masses are kept on x-axis. And the way the formula comes out, that is a way mathematically we say that is weighted average. That is weighted average. That's a typical average. That is weighted average. We'll be talking on some Thursday about that. Similarly, if we have done on the x-axis, so now you know the formula. In short, when we are writing in short, x equal to sigma mx by sigma m, or m1x1 plus m2x2, m3x3, the mass and corresponding weights divided by m1 plus m2 plus m3. Okay, so thereby we remove this. Similarly, our common sense says, if in place of x-axis, I put masses on y-axis, y-axis, m1, m2, m3 with y coordinates y1, y2, y3. The student can easily see that if I turn this bar, make x-axis vertical and y-axis horizontal, a similar calculation will be coming up, which will be giving us the y coordinate of the central mass when the masses are present on y-axis, and that will be sigma my by, so to say, sigma m, which upon elaborating means that is m1 y1 plus m2 y2 that goes on by divided by 1 plus m2 plus m3 plus m3. Okay, I think our video will be done. Otherwise, we should have continued with our discussion. We shall be doing it in the next video. So if you have gone up to this, so don't waste time. You just go to my immediate video, that is center mass or central 2, central mass 2 for this. So that will be having a continuation, and you will be learning it without break.